In this video, we're going to review how to name inorganic compounds. And in order to be able to name them, first we have to be able to determine whether it is a covalent or ionic compound, because the naming rules are going to vary depending on the type of compound that we are considering. So the first thing you'll want to review is which region of the periodic table contains the metals, where the nonmetals are, and where the metalloids are. And that's what the first image of the periodic table shows us. The yellow side of the periodic table contains the nonmetals. For ionic compounds, we also need to consider the charges of each individual ion. And it's important to keep in mind that in group 1A, all of the elements will have a +1 charge. In group 2A, all of the elements will have a +2 charge. Group 3A will have a +3 charge. These are all losing electrons. Group 5A will have a charge of -3. So once we get to that region, they are all gaining electrons. Group 6A will have a charge of -2, and group 7A will have a charge of -1. Group 8A contains noble gases. These are inert, so they very rarely form compounds. You will not see these very frequently in a compound form. 4A, it's not really easier to lose 4 electrons or gain 4 electrons, so these are going to share electrons, and they tend to form covalent compounds. And recall that covalent compounds don't have charges, so when you form compounds with carbon, for example, they're all going to be covalent and they will not have a charge. In the middle, we have all of our elements that end in B. These are what we call transition metals. And they will form charges. They're going to lose electrons to form cations, but the charges vary. And for most of them, we don't really know what the charge will be, which means that needs to be indicated in the name. So for all of the representative elements, all of the groups that end in A, which I'm going to highlight right now. So everything I'm highlighting is a representative element. For these, the charges are predictable. They're always going to be exactly the same. For transition metals, the charges will vary, and we need to represent that in their compound name. Let's take a look at naming some covalent compounds. So compounds that contain only nonmetals are covalent, which means you're looking at the yellow region of the periodic table. If any of these are bonded to each other, they are covalent compounds. And since covalent compounds come in together and they share electrons, they don't have charges. And because there are no charges, well, we're not going to indicate any kind of charge in the name because they don't exist. So let's take a look at some of the naming rules for covalent compounds. The first nonmetal in the formula will just have the same name as the element. So it will be called by its element name. The second nonmetal in the formula will have the standard base name of the element, but it's going to end with IDE. So we're going to change the ending of the element name to IDE. And the issue with covalent compounds is that because we don't have charges, we don't have a way to indicate how many of each element is in the formula. So we're going to use prefixes to do that. So when there are 2 or more of the same atom in the formula, we will use prefixes to indicate how many there are. So let's take a look at the prefixes that we're going to use. And these are distinctly different from the prefixes we use in organic nomenclature, which is where a little bit of confusion tends to happen. So if there's one element, the prefix is mono. If there are 2 of the same element, the prefix is di. 3 is tri. 4 is tetra, 5 is penta, 6 is hexa, 7 is hepta, 8 is octa, 9 is nona, and 10 is deca. The other rule where inorganic nomenclature differs from organic is when two vowels appear together. The first vowel is dropped. For example, if we had a name like carbon monoxide or carbon monoxide, which is telling us that we have one oxygen in the formula, we would drop that first O and that would become monoxide. One last rule, and that is that the prefix mono is not used for the first non-metal in the formula. So the first element in the formula, even if there's only one of them, we do not use the prefix mono. For example, if we had SO2 as a formula, we would call that sulfur dioxide, not monosulfur dioxide. So for the first element, we just drop the mono. Let's try a few covalent compounds that we can name. So let's take a look at these. Okay, the first one, this element is carbon, and the first element in the formula is just called by its standard element name. The second element is oxygen. But we said that for the second element in the formula, we are going to keep the base name, but end in "ide." So oxygen is going to become oxide. The other thing we have to pay attention to is that in the formula, we have two oxygens, so we need to use a prefix to indicate that. So we're going to use the prefix di to indicate that there are two oxygen in the formula, and we're going to end in oxide. And that name becomes carbon dioxide. Let's take a look at the second one. It's also starting with carbon, but the second element in the formula is sulfur. And we can keep the base name of that element, but we're going to end in "ide." So that will become sulfide. And since we have two of them in the formula, we're going to use the prefix "di", and that becomes carbon disulfide. In the third example, we have boron, and the subscript is telling us that we have two of them in the formula. So we're going to call this diboron. And then it looks like we have an oxide at the end. So keep in mind that second element, we have to change the ending to IDE. But we have three of them in the formula, so we will call that trioxide, and that name becomes diboron trioxide. Sometimes confusion occurs where students use, this will make more sense when we talk about the inorganic nomenclature and we get into transition metals. And then students tend to indicate the charges of different elements in situations where they don't apply. So keep in mind that covalent compounds do not have charges, which means you're not going to be indicating any kind of charge in these formulas. Let's try one more. Okay. So the first element is nitrogen. But keep in mind the subscript tells us that there are two of them in the formula, so I'm going to use the prefix di, and that becomes dinitrogen. And then the second element is oxide, but there are 5 of them, so I would use the prefix penta and the ending oxide. And here's where you have to remember that when two vowels appear together, we drop that first vowel, so this will just become pentoxide. So the name of this one would be dinitrogen pentoxide. And that's about it for covalent nomenclature. This one tends to be simpler than the ionic. Now that we know how to name covalent compounds, we will move into naming ionic compounds. So the first important part is recognizing whether the compound you're looking at is ionic or covalent. And if you have a metal bonded to a nonmetal, it's an ionic compound. So if any of the elements highlighted in blue are bonded to an element bonded in yellow, that will be an ionic compound, and you will use ionic compound naming rules. Keep in mind that the elements that I've highlighted here in blue, these are all representative elements. And with representative elements, the charges will be incredibly predictable. They are always the same. And since the charges of representative elements do not vary, there's no need to indicate the charge in the name. So if you're using representative elements to form a compound, those charges are always the same. You do not need to indicate that charge in the name. Before we get into naming, it may be helpful to just review how the formulas are formed so that you understand what the ions are when you go backwards. So let's choose a few elements from the periodic table. We can take magnesium, for example, and notice that magnesium is in group 2A, which means it will have a charge of +2. So I'm going to take my magnesium ion, and then I'm going to bond it to another ion. Let's take oxygen, for example. Oxygen would have a charge of -2 because it's in group 6A. If these were to form a compound, notice that the magnesium charge is +2 and the oxygen charge is -2, which means these charges will cancel out. So when you form a compound between them and you write the formula, it would just be MgO because the charges cancel. Let's try an instance where the charges don't cancel. So for example, we could take magnesium and bond it to, let's try nitrogen. Nitrogen is in group 5A, which means it'll have a charge of -3. Whoa, I did not mean to move that. Okay, there we are. So here the charges don't cancel, which means in order to form a formula, I'm going to write the cation first, the anion second, and what we can do is cross the charges over. So the 2 will come down behind the nitrogen, and the 3 will come down behind the magnesium. When you form a chemical formula out of 2 ions, you actually don't include the charges in the formula anymore. So you just include the number. So this would be Mg3N2. Because these charges didn't cancel, we just crossed them over. And really what this is telling us is that there are 3 magnesium ions in the formula. And there are 2 nitride ions in the formula, and each one has a charge of -3. Notice that when you break it down like that, this compound will have a charge of +6 and a charge of -6, and these charges cancel, which gives us a neutral compound. This is why that crossing over method works. The other thing to keep in mind is, well, it'll be easier if I just demonstrate. Let's take our magnesium ion and give it something that will have a -1 charge. So any of the halogens, for example. I don't like how it's moving that. Okay, I will take chloride. Chloride is in group 7A, so it'll have a charge of -1. I'm going to put these together. And we could do this the same way. I can write the cation first, the anion second, and then I can cross the charges over. When I cross the charge from magnesium, the 2 is going to come down behind chloride. When I cross the charge from chloride, the 1 comes down behind magnesium. But keep in mind that when your subscript is 1, we typically don't indicate that in the formula. So we would just write this as MgCl2. And that's about it. So that's a basic review of how to generate a formula. Now that we know that, let's get into our inorganic naming rules. So we're going to name inorganic, or let's be more specific, ionic compounds with representative elements. And that's important because we said the representative elements, the charges are not going to vary, so we don't need to indicate that in the compound name. So we're always going to list the cation first, then the anion. And the rules will be the following. So naming cations, the cation is just going to be the element name, which is really nice. You just copy the element over and that's it. With anions, we are going to change the ending. Just like we did in the covalent compounds. So we are going to keep the base name of the element, and we're going to give it an IDE ending. And then we put that together. So for example, if we had, let's say that ion, that's a sodium, and we would just call that, well, sodium. If we had an anion like that, well, that comes from nitrogen, but we want to keep the base name and end with IDE. So that will be called nitride. And if we formed a compound between these two, we would call it sodium nitride. So let's try a few compounds and practice that. Okay, so let's try that one. This is magnesium. That just comes directly off the periodic table. And this element is called chlorine, but because we would need to end with IDE to indicate that it's an anion, we would call that magnesium chloride. So we're keeping that chlor base name and we're giving it an IDE ending. The other thing to keep in mind is when you're writing these formulas, the cation is always listed first. So magnesium has to have the +2 charge. And the anion is always listed second, so chloride needs to have the negative charge. There are a few different ways you can figure out the charges. You could go backwards and uncross the charges. So here, because there's nothing listed after magnesium, that would be a subscript of 1, which we always omit when we generate the formula. So I could take the 2, give it back to magnesium, and I could take the 1 and give it back to chloride. Since magnesium is listed first and it's a metal, we know that it has to be a cation, it has to have a positive charge. So that will be a charge of +2. Chloride is listed second and it's a nonmetal, so it'll be an anion, which means its charge is -1. The other way we could have thought about this is, well, we could look at the periodic table. We see magnesium is in group 2A. It has to have a charge of +2. And chloride is in group 7A. It has to have a charge of -1. So you could either uncross or you could just look at the periodic table directly and figure that out. Let's try a few more. All right, the first one just gets the element name, and that's sodium. And sodium has a charge of +1, which means that 3 goes back to nitrogen, which we could also figure out by looking at the periodic table. Since nitrogen is the one with the negative charge, it's an anion, it's always listed second in the formula, that's the one that's going to have the IDE ending. So I'm going to start with my nitrogen name. I'm going to keep the base name and end with IDE, and that will become sodium nitride. Notice I'm not indicating any charges in these names, and that's because they are completely predictable. I can just use the periodic table to go backwards, and I don't really have to think about it any further. Let's try a few more. The first element in the name will just be called potassium. This is the one that's commonly confused because it doesn't start with P, which is kind of what you would expect for potassium, but it's just K. The second one comes from phosphorus. But keep in mind that it's an anion with a -3 charge. So we are going to keep the base name and end in "ide," and that will be phosphide. So that one is just called potassium phosphide. Couple more. All right, this is one where the charges are actually a little bit tricky. Here it looks like the charges actually canceled out because if you look at the periodic table, calcium is in group 2A, so it has to have a +2 charge, and oxygen is in group 6A, so it has to have a -2 charge. These charges canceled out, which is why they have a 1-to-1 ratio in that formula. So we could put subscripts of 1 here, but we don't really need to. We just omit those. So here's one example if you wanted to figure out the charges, you couldn't just uncross the formula. You would have to use the periodic table to figure that out. So calcium has the positive charge. I'm just going to call it the element name. And oxygen needs to have that IDE ending because it's an anion. So we're going to call it oxide. And that just becomes calcium oxide. Okay, let's do one more. Let's make that a little bit interesting. Okay. So here we could uncross charges. We could give the 3 back to aluminum and the 2 back to sulfur, which would give us a +3 charge on aluminum and a -2 charge on sulfur. And we could also, of course, figure that out by using the periodic table. Aluminum is in group 3A, so it would have a +3 charge. And sulfur is in group 6A, so it would have a -2 charge. All right, so since aluminum is the cation, I'm just going to call it by its element name, which is aluminum. And sulfur is the anion, so it needs to have that IDE ending. So I will keep the base name, and then I will change the ending to IDE, and that becomes sulfide. So the name here is aluminum sulfide. And that's pretty much it for naming elements or naming ionic compounds with representative elements.